All right, are there any questions on anything like the homework?
Yes. Dual problems.
How you calculate what? Okay, let's look at that. So that was the one due here? Oh wait, is that the right class? Yeah, that's the right class. Oh wait. Now notice, yeah. At the end of the semester when your projects are due, there won't be homework. So don't start freaking out. Did you say you feel ripped off?
Yeah.
No, you said I'm ripped off. All right. Oh, are you serious? You need me to input common mode range? This is a challenge? All right. Did you see that here that this device was a 20 by 2 instead of a 10 by 2? So let's go draw it. Why does it matter it's 20 by 2?
Because it's there.
Then I get what current flowing through there? 2 times what was the current for these sizes in this problem?
40 down there and then 20.
All right, you're challenged by the input common mode range. So what's the minimum voltage I need here that's common to the 2 inputs? VGS, and what's the minimum I need across the cascode, the wide swing cascode? So what is CMR min? Okay, first part of the common mode where input is done. This has to stay above this voltage in order to give you enough pressure for these to turn on and this to turn on. Wait, what? These, the common mode voltage on the input of the diff amp. They have to stay at least 1.55, so you have a 1.05 there and a 250 across each of those. Yay? All right, and then what about the other direction? This is VDD. VDD, it's probably 5 volts. We can put that in later. So in order for these transistors to stay in saturation, we need VDS to be greater than or equal to VGS minus V threshold N, or VD minus VS greater than or equal to VG minus VS minus V threshold N. Those cancel. VD is what? And then this is our input. V gate is our max input common mode range. And so our VG, or our common mode range max, is equal to VDD plus V threshold N. In this case, that could be equal to 5.8 volts. So now you can understand why you say that was hard, and I'm like, what? We even went over this in class, and it's in the book. What? You have to look at the book? What's wrong with that? All right. Any questions on that? Who understands that? Let me look at today's quiz now that you've scared me. Did everybody do well on... Oh, I didn't hand back that stuff, did I? Today's quiz is a diff amp. And it is open book. I don't know. I think it's easy. What do I know? Let's pass these back. Nobody else has homework to turn in, right? All right, I'm putting the rubber band on. All right, is that the only thing on the homework that you didn't follow, or is there something else on that problem? Okay, let's do the AC drain currents and AC gate source voltages, etc. I think that's it. Any questions? You mean the input common mode range?
Well, for the second one, I asked you to simulate the range of the output voltage.
You mean this one?
Yeah.
It's you just sweep one of the inputs with the other one held, and then if you hold the, actually let's do that too. I want to make sure you get this for your projects. But let's do the AC first on that one. And the gates have AC 1 millivolt minus 2 millivolts. You hate it that I make up my own problems. You rather I use the book ones where the solutions are online.
Yes.
I know. Wait, what was this AC voltage here again? And this one was? I just picked values just so you could simulate and do hand calculations. All right, so stupid questions. What's this voltage here? What's this voltage here? Plus minus VGS, plus minus VGS. Here I am, I'm gonna start walking. I go up at 1 millivolts where I start walking, then do I go uphill or downhill? And here I'm at, standing here. Do I go uphill or downhill? And then here I've got plus minus 2 millivolts. So what do I do here? Minus, the way I've drawn. Anybody agree with that? So now I know that if I move these over, I get 3 millivolts equals VGS1 minus VGS2. However, VGS1 and VGS2 have to be equal and opposite. Why? This current's GM VGS1. This current is GM VGS2. And I know no AC current flows through my tail current, so I didn't even draw that. So if this was biased at 20 microamps and I said the GM VGS is 1 microamp and positive, then that means it's going up to 21. That means this would be negative and it would go from 20 to 19, so the sum stays. So when it's a negative, it's going back this way, and when it's positive, it's going this way, and these always have to sum to the 40 microamps. The ACs always have to be equal and opposite. So if this goes up by 1, this has to go down by 1. So that's how I know that's true. So what is VGS1 equal to? And what is VGS2 equal to? Anybody follow that? And I can know that GMs are what? And so ID1 equals GM times 1.5 millivolts, which equals 2.25 nanoamps. 225, yeah. 220.
225.
You know, I should not listen to you. I should just look at it myself. Anyway, and then ID2 equals GM times minus 1.5 millivolts, which equals minus 225 nanoamps. There's, we got the DC, the AC. The DC currents are 20, 20, and 40. DC voltage is 1.05. Any questions on that one? And that was hard, huh? No one's playing with their phone right in front of me, right? Juan? I might have to take that away, man. My phone.
My phone. Oh, man.
All right. Any questions on the first problem that we did in like total of 7 minutes? I'm feeling like I'm ripping you off. Was that problem easy?
So wait, what does that say for number 2? When I was asking for like the gain be out.
I'm gonna do number 2 next, man. Give me a break. Here. All right, we ready for number 2?
Yeah.
Everybody's got number 1 down, so on the final exam or quiz, they'll be able to do it. Yeah, maybe.
Maybe.
You know, I always take quizzes from the homework. That way, when you've done the homework, you get rewarded. And when you don't, you don't.
Is the quiz of CMOS?
Yep. All right, so let's do this. I think it's the same problem just with the current source load, right? Oh, what's the input common mode range? Does it ask that?
Yeah.
And what is it? What is the common mode range min? I didn't change anything down here. It's the exact same thing. Okay, and then what? This have the same source to gate voltage. They're physically tied together. Same DC drain currents. So this voltage is what? It'll be the same as that one. So then I write V drain to source has to be greater than or equal to V gate to source minus the threshold voltage, or V drain has to be greater than V gate, where I didn't show the VS. But now V drain is what? That's greater than or equal to VG minus V threshold N. So common mode range max equals VDD minus VSG plus, boom, done. Yay or nay? All right, let's do the gain again, but instead of doing it the exact same way, I'm going to do it a little bit different. Why don't I call this VN1, VN2 plus minus VGS1 plus minus VGS2. So I get VN1 minus VGS1 plus VGS2 minus VN2 equals 0. Or VN1 minus VN2 equals VGS1 plus or minus VGS2. Or based upon our previous discussion where the currents have to be equal, what can I say? Correct. VN1 equals VGS1 plus VGS2 over 2. Anybody agree with that? All right, whoops, I got a sign mistake there, don't I? What is my sign mistake? Yeah. Wait, so, yeah. So let me think about that for a moment. If I put the same voltage here and I move them back and forth, then VGS1 and VGS2 are. If I make the same voltage on the gates of M1 and M2, then V1 and V2 are equal. If they're equal, what? And this V1 is 0, effectively, right? Well, wait a sec, let's back up. If I put the same voltage here,
No, it's 2 times.
yeah, I need to write this a little different. I don't like this equation. If I put the same voltage here, wouldn't everybody agree then that what is V1 minus V2? 0. And what's the current I get? 0. In other words, I am not amplifying a common voltage. I'm only amplifying the difference. So I have to have a difference on the two inputs. Yay or nay? And if that's why it's a differential amplifier. All right. So I'm going to write now, using this and what I had, VGS1 equals V in 1 minus V in 2 over 2, and VGS2 equals V in 1, or minus, let's write like this, minus V in 1, or let's write minus VGS1. Let's keep it easy. All right. So the current that flows here, and actually I'm going to do it from scratch because I want you to understand this. Any questions on this? Nick, any questions? All right. How are the Vegas Knights doing anyway?
You're up 3-1, baby.
So how many games are there before they...
You have to win 4. 7.
All right, and then the next ones are going to be in San Jose?
Yeah, the next one's in San Jose. The one after that is here.
Okay.
And it's a lot of fun to go, man. This.
I'm sure it's fun when they're winning and you're not tired.
I get up at 3 in the morning, dude. I'm always tired.
And you still go to Sharks games. All right.
No, I go to Golden Knights.
All right. Or night games, yeah. Oh, well, now you made me mess up my paper here.
And about Johnson.
And you're taking a class from me.
There's a lot of my thing. And then
All right, so let's just leave it like this. Let's call this V in 1, V in 2, plus minus VGS1, plus minus VGS2. I'm going to put the batteries here so we can go nice and slow. V in 1, battery here, plus minus V in 2. It makes common sense that if we move these together and they're equal, that we won't amplify the difference, but let's prove that. Let's go over here and write this nice and slow. Start running from here. So I get V in 1, and then I go down, minus VGS1, then I go up, plus VGS2, then I go down, minus V in 2, equals 0. Anybody agree? All right. Then I say V in 1 minus V in 2 equals VGS1 minus VGS2. Looking good. But I know this current GM VGS has to be equal and opposite to GM VGS2, or in other words, GM VGS1 equals minus GM VGS2. Give me an explanation why. Because no AC current's going to flow down there.
current goes up.
Yeah, so the overall current here goes up, the overall current here has to go down. When the overall current here goes down, that's the same as it being a negative AC current. So if this current went up by a microamp, the AC would be up by a microamp. This would go down by a microamp. And so I'd say the current here is minus 1 microamp or positive 1 flowing opposite of the arrow. That's really clear to me, but is it clear to you? All right. No. Okay, one more time. So I have 20 microamps here and 20 microamps here, DC wise, right? So now if I put a wiggle in here and I push this voltage up, and let's say I push this up and I turn this device on, that causes this current to increase to go from 20 to 21. So I say the AC current here is 1 microamp. So I would write here, for example, ID1 equals 1 microamp. Here, however, when I pull this up, this goes up, assuming this stays at 0, doesn't change. If this goes up, that causes the VGS of this to what? Go down. And if it goes down, what happens to the current here? It goes down, and it goes down by minus 1 microamp, which means this would go from 20 down to 19. So I say the AC current's minus 1 flowing down here, which means it decreases from 20 to 19, or positive 1 going this way. So I sketch and I say, oh, my AC current here is 1 microamp, but that's understood to cause the overall current to decrease, because you can't have the current flowing backwards. Everybody follow that? So if this would mean VGS1 equals minus VGS2. So I'm going to come down here, I'm going to plug that in, and I'm going to write 2 VGS1. Who agrees with that? Or VGS1 equals V in 1 minus V in 2 over 2. So now I'm going to use this result, and VGS2 would be minus V in 1 minus V in 2 over 2, or V in 2 minus V in 1 over 2. So now I'm going slow. I'm going to do this on the next page where I don't have all the clutter. So then over here, when I draw my circuit, I've got my V in 1, V in 2. The current that flows here is V in 1 minus V in 2 over 2 times GM. What's the current that flows in here? It's the same. It flows like that. But I would say the drain current here is minus V in 1 minus V in 2 over 2 times GM. So going down, it's minus, but here I think of it going around. The 1 microamp increases here, and it causes it to decrease over here. Does anybody see that? Marco. After about 100 times, that's funny, but then after it's not so funny. I'm sure Marco would agree with that. I know, it's not, it's like, eh. All right. Okay. So I have a current here flowing, going up of GM. But now notice the current action here and here. So what's this current equal to? It's the same as this one. It's V in 1 minus V in 2 over 2 times GM. And the current flowing in here is the same thing. So what's the total current flowing into R out P and R out N? What's this total current flowing in like this? Oh, yeah. So V out over V in 1 minus V in 2 is equal to GM R out P in parallel with R out N. Everybody agree with that? What else is there to do on that problem? Plug in the numbers. So it's R out P in parallel with R out N. 2.22 meg, what is GM? 150, and then what's V in 1 minus V in 2? Isn't it minus 3 or minus 1 milli or something? I don't remember. Let me look. It would be 1 minus minus 2 or 3 millivolts. Yep. And so then your gain would be 3 millivolts, so your output would be 3 millivolts times GM times R out P in parallel with R out N. Any questions on that one? Quiz today. So let's do output swing and how we show that in simulations. Touching your phone. I wish I would have kept my flip phone. All right, which I got when I was about 40. Okay. All right, let's do this one. All right, I'm going to do this, see if it makes sense. Yeah, I can think of lots of ways of doing it. You tell me. This one I'm going to put on the gate plus minus VCM. Looking good? So what is this voltage here? You're killing me. I don't give hard problems. They're all easy problems. It's VCM minus VGS, right? So what's the minimum voltage that I have to have across this device? So what's the minimum voltage I can have on my output? Isn't going to be dependent on what the inputs are. If I assume they're both at VCM and I CM and I swing and I ask what's the minimum output, it's going to be VDS sat plus VCM minus VGS. Am I making it too hard? Or does it look too easy? And what's the maximum output? What do I need to have here? What's that? Boom, done. Okay, so now, how do I show that? Or any questions before I talk about simulations?
So VCM is what we input to both of them, or just
No, I'm going to go over that in a sec. For just the swing, you have VCM on the two inputs, right? So now I want to be able to simulate it. So let me ask this. Does it matter for the max what VCM is? No. But how do I simulate things? Oh, by the way, what is the gain of this diff amp that you calculated? 333? So if I put in 10 millivolts on one of them, won't the output swing by like 3.33 volts? So here's what I'm going to do for one example. I'll put this at 2.5 volts, and then I'll put this at 2.5 volts, and then I'll go up, say, I got to make sure I don't go up too high. I'll go up maybe 5 millivolts. And then I'll see this start to go up, and then it'll saturate, it'll start to roll off. Right? And then when I go the other way, so I might put a DC sweep in here from 2.495 up to 2.505. And when I go the other way, I'm going to see it kind of roll off. But what's the slope of this line as I change one of the inputs? What's the slope of the output as I change one of the inputs? What is dV out, dV in equal to? You're killing me. The gain. GM R out N in parallel to R out P. Well, I'm changing V out with a change in V in. Isn't that the gain? Isn't that the derivative? And so when it starts to flatten out, what does that mean about the gain? It's starting to drop, right? That means you're starting to move the devices into triode or cutoff. So I sweep that and I show and I go, oh, here's my max output, here's my min for that particular common mode voltage, but then I could change my common mode and do it then and show that the equations are still valid. Am I making sense?
Is that like how we get high gains, just have a steeper slope?
Yeah, you go to steeper slope. That occurs when the two inputs are near each other, right? Because as they start to move apart, you start to get ultimately a reduction in the gain. It starts to roll off. That's why distortion is a problem. Okay, are there any quick questions on homework? I want to get back to band gaps. And then I want to talk about the project. All right, good? Okay. So, let's real quick go over the parasitic vertical PNP. Parasitic means that it's inherent, it's built into the process, but not a parameter that you get in, they'll characterize them almost now, because of band gaps, almost always nowadays. But what it is you take and you make a N-well in a P substrate, that's the material, and then inside of that you have a P plus. And then how do you connect to the N-well, people that have taken 421, 621? N plus. How do you connect to the P substrate? P plus. Right? And then you have a parasitic PNP, where your collector is the P sub, your base is the N-well, and your emitter is the P plus. And if you think, why not make a NPN and try to use it the other way, you will see that that's not possible. Because what's the substrate always? Well, most integrated circuits. Ground. All right, so when I draw this, or look at in the layouts in the book, I'm going to connect this to ground, this to ground, so those will be tied together, and this will be the cathode of the diode, or I get something that looks like this. And this point are, somebody said it, same. I just think of the PNP as a diet. Am I blowing everybody's mind with that discussion? All right, we're ready to talk about, let's actually, before we do the band gap, let's do the thermal, the P-tap one more time. All right, you should be able to help me do this pretty fast. Would you be disappointed if there wasn't a quiz today? Don't worry, there is. Quizzes make you feel alive, don't they? Or do they give you anxiety and stress? You know what? Whoops.
I'm feeling with the next.
All right.
Nothing else gives me anxiety.
All right. Remind me, why do we put K diodes in parallel? Decrease the voltage drop, and we called that voltage drop what? And what do we call this voltage drop? And then what's that voltage? And so we can write VD1 is equal to NVT natural log ID over IS. VD2 is equal to NVT natural log ID over, am I in my own little world up here? What's it over? All right, don't let me stay in my own little world. Okay, and what's the current that flows? Looking good? That's the current that flows in here. Well, we can do it like that. How's that? Stay consistent. And that's equal to NVT natural log of K over R, right? If we take those and we do this, and we go to L times R, and we call that our reference voltage, then what do I know about the current in this device? It's mirrored over here, and it's this current, and so I write Vref is equal to L times R times NVT natural log of K over R. The R's cancel, and I get Vref equals L times N times VT. And L would mean that I've got L of these resistors in series. So here would be R. Oops. This would be a resistor of 2 times R, right? And I have L and VT natural log of K. And then what's the only thing that's going to change with temperature here? VT. So we get L times N times V natural log of K times KT over Q. When I take the derivative, this term, the derivative of VT with respect to temperature is equal to 0.085 millivolts per degree C. And we called that what? No, what do we call a voltage reference that increases in value with temperature? PTAT. So just to make sure I'm not in my own little world up here, which is maybe the case, why would I ever want to design a circuit that has a voltage that increases with increasing temperature? Measure temperature. Or I would want it to be like, oh, when I get to a certain voltage, I know things are too hot, I need to slow down the processor in my phone. And everybody knows, so I have a laptop that I've had for about 7-8 years. I hate to buy new computers because they always turn into junk. And the laptop performance kept getting poorer and poorer and poorer. And I'd look at the processor and it's running slower and slower and slower. And I'm like, what's going on? So I finally got on YouTube and I took it apart and I determined that the heat tube was broken. And so the heat tube on all modern processors is what removes the heat from the chip. So I ordered a new heat tube on eBay with some silicone thermal grease. And I put the new heat tube in there, and then now it's running as good as new. All right, because that's how they handle when things get too hot, is they slow down the performance. The tube must have cracked or something inside because the heat wasn't being propagated through. And I say that, and I wonder to myself, how many people here know what a heat tube is for a processor? Come on. Let's see. That's kind of what they look like. Heat pipe. That's a better heat pipe. Let's use that. Yeah, like that. They come out, but they have a, let's do Intel processor. I put my specific processor number in, and so it'd pop up for the particular heat tube. These are a little bit more fancy than what mine was. Mine didn't have kind of like that. Didn't have a fan, but that's for really getting heat out of the processor, a really big one. But, whoops. That's what happens. You can actually see, and you can get that on your phone too. And there's apps you can run on your computer. All right, so it's a big deal. If you don't do that, then it's better to have a slow computer than no computer at all. All right, so are we ready to do a band gap? So I'm going to use this result, that the current that flows is VT natural log ID, and instead of having just this LR, what I'm going to do is I'm going to put another diode here. Okay, and so I'm going to take the same circuit on the next page. The problem is, when you learn how to fix stuff, you end up fixing everything yourself. I mean, holy crap.
That you did that either.
And then, yeah, your neighbors know, and then, oh, man.
Plus, everybody knows you don't know how to work in cars, you don't know how to work.
Then all you do is work on cars. All right, so this is the V band gap. And this current here is L times N times VT times natural log of K. Especially people that can't even set up their wireless access point and stuff like that. Holy crap. Whoops, this L isn't in here yet. This is, whoops, it's NVT natural log of K over R. Like this. All right, looking good? So now what is the band gap voltage equal to? It's equal to L times R times NVT times natural log of K all over R plus V diode. Does anybody agree with that? So you notice the resistors cancel, and then I get the band gap voltage is equal to L times N times VT times the natural log of K plus V diode. So now the key takeaway is this is a PTAT and this is a CTAT, because what did the diode voltage do as we increase temperature? With constant current? Goes down. So we're going to add those two together, but we've got to figure out how to select K and L and all that. So tell me what to do here. I want to set the temp code to 0. I want the variation in the band gap voltage to be 0. Take the derivative. So I'm going to take the derivative of this with respect to temperature. When I do, I have L times N times natural log of K. And what's the derivative of KT over Q with respect to temperature? K over Q. And that's the K of number of diodes in the lowercase. I didn't make those up. And then the derivative of this would be V diode with respect to temperature. And this we know is minus 1.6 millivolts per degree C roughly. Now, when you do these in real life, they characterize the parasitic PMP in every CMOS process, so you know precisely how this behaves. It's not going to be exactly 1.6, and you're going to know exactly the layout that they use in the currents and how they vary. They will provide you models for the parasitic PMP. So when you do your design, you're not guessing. Okay? So now if I look at this, I want to set this equal to 0. And so I'm going to pause, and we're going to do a PowerPoint here, and I'm going to pull that up in the book. And here I used K diodes. I basically just want the 0.7. You don't need to use K, you can use 1. And you look and you take the derivative, you get your minus 1.6 plus your L and natural log of K times K over Q, but K over Q is 0.085. That means if you solve for L, you get L is equal to 9.41. And so when those are equal to 0, so you set A equal to 0 and solve for it. And so if you look, there's various examples of band gaps in the book and how they vary with temperature. And if somebody asks you, these are what you should take away. They shouldn't ask you anything too much more complicated than this. If they ask you, how does a band gap voltage reference work? Band gap voltage reference works by adding the PTAT, the thermal voltage reference, increase in temperature with increasing temperature, to the CTAT, and the CTAT is the diode voltage. Remember, the diode voltage decreases for a constant current with increasing temperature. So the simple answer is you add a PTAT and a CTAT together to get 0 temperature. They ask you, why is it called a band gap? It's called a band gap because the band gap energy of silicon does what with increasing temperature, people in 450? It shrinks. Well, wait, let me ask you this. You know what an energy band diagram of a PN junction looks like, right? Okay, so if I ask you what does the built-in potential of the PN junction do with increasing temperature? Goes down. So I don't need to apply as high voltage to overcome the potential barrier. That's why my diode voltage decreases with increasing temperature. It shrinks, the barrier drops. So in order to flatten them out and get conduction, I don't need to apply as high voltage. All right, we good? There's some stuff in the book about low voltage band gaps, but I'm not going to go into that because I want to spend the rest of the next 20 minutes on projects. Are there any questions on that? Anything we've covered? What's the next homework? Let's look at that, make sure you're all prepared. Next one's due on Monday. Ooh, nice. What does that look like? How a Schottky diode varies. And there's our Schottky diode model. Then what's here? Oh, we're using Schottky diodes to generate a reference voltage. Ooh, you're actually using what you learned in class. All right, let me ask a few questions here. What's the point of these MOSFETs here? Current mirror. I was lazy and only drew one, but here's 2, cascode. What about these? Current mirror to force that this voltage, we'll call it, why don't we call it, how about V diode 1? Is this voltage over here, V diode 1? How many Schottky diodes here do I have in parallel? 8. So what do I know about V, assuming the same currents flow on each side? V diode 2 is, then V diode 1. Less. Why? I've got 8 of them in parallel. Current splits. Oh, well, wait, all that stuff he did. Now I know why. Then you have to calculate the tempco too. So you calculate the reference voltage and you calculate the tempco. Use what we learned in class. Isn't that what happens? You want? I got to give it a little difference. I got to use a different type of diode. And you have to determine what the Schottky diodes does with temperature, so you don't use a regular diode. So if you use minus 1.6, ain't right. Okay, let's go talk about projects. Unless you'd rather just take the quiz. All right. So I want to talk about what's challenging here and give you some suggestions on how to approach the projects. So one of the challenges is, where is it? 2 VDD down to 2 volts. Okay, so one of the issues that you're going to face is that when you go to such a small VDD and you use a normal diff amp like we covered at the beginning of the lecture, you need to have a voltage drop, let me pull it up here and discuss it, and I'll tell you an approach. And you don't have to use my approach. You're the designer. You do what you think. But you have to use an approach where you can have a lower VDD. So if I look at this right here and I ask, you notice that here, with the sizes that I have, this is going to eat 1.15 volts by itself. Does everybody see that? Then I need to have, with the device sizes that I have, another 0.25 up there. So now just from here to here, we're already up to 1.3 volt, 1.4 volts. Then if I have a simple current mirror here, I have another 0.25, so I'm already just with that down to 1.6 volts just to be on the edge. So I want to make sure I have a larger margin. So I'm going to suggest some circuits for you, all right? Now, note that this will work. Don't get it, you can get it to work, but it's easier if you pick an overdrive voltage that is low. So if I pick say I pick 50 millivolts, what would be the VSG here? If I have a 50 millivolt overdrive or excess gate voltage or whatever you want to call it, VSD SAT, 0.95. Then if I have 50 millivolts, 0.05, 0.05. Well, now using this basic current mirror, life is good, right? Because now I have a volt roughly to go from here to here, and I have a volt left to swing for my circuits to swing around. Everybody follow that? Any questions? Okay, so let me give you some other suggestions here, and then I'm going to go through the topology. I'll use the basic diff amp to go through the topology. So I want you to think about the following. If I think about this topology, what is the minimum VDD that I need? So I've got a VSG. Now, do I use 1.15? Of course not. Those are just for the examples in the book. You're designing and setting the overdrive voltage. So you might end up with a 50 millivolt overdrive. This would be 0.95. So what's this voltage right here? VDD minus VSG. Now what do I need across each device here? This voltage has to be greater than what? 2 VDS SAT. Everybody agree with that? Now, let's take and do the following. And let's go crazy. Let's go like this. And now let's make these times 2. And I want to pause and go through the biasing. Okay, so whatever bias current you've selected, what is the current that flows in there? 2ID. What's the current that flows in there and there? I. And if I look and I've got the bias, what's the current that flows in there and there based upon times 2? So wait, I got a current here that flows, which is I, and a current here that flows, which is I. So what's the current flowing in each of these? I. Now, if I ask, what is the minimum input voltage with this topology? I'm going to calculate it for you. What is this voltage right here with the wide swing bias? VDS sat. Everybody agree with that? So if I look, I'm just going to look at one side. Here's VDD. I need a VSD sat here. And I've got my transistor going over, and then I've got VDS sat here. And then I'm going down in my common mode range min on the input. Let me see, I know that VSD has to be greater than or equal to VSG minus V threshold P. Or V source minus V drain has to be greater than or equal to V source minus V gate minus V threshold P. V sources cancel, multiply both sides by -1, and I get V drain has to be less than or equal to V gate minus V threshold P, or plus V threshold P. And then this would be my min voltage. What is my drain voltage? VDS sat. And so it says my input has to be, here, let's write it this way. VG has to be greater than or equal to VDS sat, or did I do this right? V gate. Yeah, that's right. Just flip the sides. VDS sat minus V threshold P. This says my gate can actually go negative in this topology. Okay? So the whole point here is this is a diff amp, and if I were to look at the output, I can do my calculation here and I get my currents flowing and I add. There may be other topologies that are useful. But I want to make sure you get going on your project. So let's go back to the basic diff amp. Are there any questions on this?
So the I from the current, the circuit on the left, where are those I's going up?
No, these are all DC biased, right? So here I get the I, it comes down and adds to this I coming down. That's why I set this to 2 times. Same thing over here. All right, so let's go look, and I want to get you a topology that you can use. So you don't want to do a 3-stage gain topology because you'll have a hard time compensating that or making it stable. All right, so here's what we're going to do. We'll use this topology, and we'll talk about wide swing topologies with a PMOS and an NMOS diff amp later if you want to go crazy. Okay, so I go here, and then I come down, and I'll keep this. I'm not going to use cascodes. Why? Well, I can use cascodes, but then if I'm going to do that, I need really small overdrive voltages, like tens of millivolts of overdrive, okay? So then I'm going to go over here, just real basic topology. And I'm going to modify this in a moment, but for now I'll just call this V out, and this is my op amp. So if I have a gain of 333 here, and I have a gain of 333 here, what's the overall gain? That times that, which is way above the requirement of 60 dB or whatever, right? Everybody follow? Now, if I look at this, this voltage should be basically the same as this, so I treat for biasing purposes as if this transistor is tied to the gate of this. But I know this node can wiggle around, and this can thus wiggle around the gate of this one. This is a common source amplifier. This is a diff amp. So any questions about how to bias this? So this is a basic op amp. All right, so now here's the rub. What happens when I put, I don't remember what your spec is, but let's say a 1K resistor there.
Yeah, go.
Instead of the output impedance being 2.2 meg, it's now 1K. So it's more than 1,000 times less than it was before. So here's what I'm going to do in my first iteration of this design. I'm going to do this. Got my diff amp. I don't want you leaving this class thinking op amps are magic. I'm going to go over here, basic design that I just had. And I'm going to isolate my output with this circuit right here. So this is a diff amp. This is a common source. And what's this one? Common drain or source follower. Anybody agree with that? So now, what's my source follower gain? Close to 1. And if it can't drive the 1K resistor and the capacitor, you know what I'm going to do? I'm going to grab and make this 100 times bigger and burn more current in the output stage so I can drive a lower load. Then my basic gain stage isn't affected by the load or the capacitance. Everybody follow that? So now, here's the problem with doing it that way. If I do it this way, what's the maximum this voltage can swing up to? Got to keep a VDS sat across this. Everybody see that? And now, if I have a VGS here, what's the maximum V out? VDD minus VSD sat minus VGS. Not too good, right? It's limited output swing. Everybody follow that. What's the minimum this node can swing down to? VDS, oh wait, but if I go to VDS sat, I don't have a VGS plus a VDS sat. So this node has to stay VGS, but I don't care about this node, I care about my output. So my output though with this can be swing down to, just to keep this one on, VDS sat. So let's throw some numbers in. If I have a 2 volt VDD, so this would be 2, let's just say VDS sat is 50 millivolts and VGS is 0.85. So what's the max output that I could have? 1.1, right? And then here, what would be the minimum output? 0.05. Remember, I'm not using the book examples. I'm not brainwashed. I'm designing this myself. Everybody see that? You like that? You like it that half of your power supply voltages, you can't use it. I don't. So, and then I'll talk about this more next time. Let me tell you what we're going to do. In order to get a wider output swing, here's what we're going to do. We're going to take, and we're going to use what's called a push-pull output. And then this push-pull output will look like this. And so in this case, if I were to tie these together, what would the, if I tie these together, what circuit is this, people that have taken 421, 621? Inverter. But now, what can my V out swing up to? And what can it swing down to? And if these are 50 millivolts, that means I can go within 50 millivolts of each power supply rail. This is good. Now, the question is, how do I bias it and all that other stuff, which we'll cover later. Any questions? Yes? No, this would be connected to, here, I'll sketch the circuit if you want. This we'll call VP CAS, VN CAS, sound familiar? And then here we'll say times 2 times 1, and then we'll put our diff amp like this. Oh, whoops. And then over here we'll have our other side of our diff amp. And then we'll have our NMOS down here. This will be times 2. And then what we're going to do, that's basically the topology, and we'll go over it next time. So this would be the inputs of the diff amp. So this is my diff amp here, or the op amp. And then this would be the second stage gain. Look fancy? I don't want you having an op amp that isn't practical and something you can discuss in a job interview. All right. Any last second questions? We ready to kick arse in the quiz, right? All right.